Okay, so hey guys, it's Quinston, and today we're going to look at the threaded binary tree. Now, what is a threaded binary tree? Now, we've looked at binary trees as a whole. This is just a modification which we do in it to make it more efficient in some way or the other. It's not a big deal though. So a binary tree is threaded by making all the right child pointers that would normally be null pointers to the in-order successor of the node if it exists, and all the left child pointers that would normally be null pointers to point to the in-order predecessor of the node. So what this means that if we have a binary tree and we find the in-order list of that binary tree, then suppose we select an element in that in-order list and that element corresponds to a particular node in the binary tree, then the predecessor of that in-order element in the list will be the pointer for the element in the corresponding node of the binary tree. You will learn this when you look at the rest of the chapters or the rest of the tutorial, and then let's just proceed without much ado and get to the code. So what does the node look like? A node in the thread binary tree. So the node looks like this. You initialize it with the class node. It's supposed to be a class. In data, there is a data box. Node left, the node left pointer, the node right pointer, the int L bit. Now the int L bit is basically an indicator. You can say that it's an indicator. When it is 1, it indicates that it basically has a child node, and if it has 0, it basically tells you that it is connected to a thread. Similarly, the right R bit. Now you have a constructor int data, this data dot equals data because you want to initialize it, and that's it. So these are basically the designations. You have data, L bit, R bit, right node and left node. This is how a node looks like in the threaded binary tree. So let's start with the main function, public static void main string args. Now at the beginning you want to create the root node, which is going to be the checking conditions. Now in the thread binary tree you have a special root node which you don't connect to any other nodes but except for one, which is a virtual root node. Let's just get to that. So the new root will contain a value. It's going to contain a random value. You can take it to be anything because it's not going to affect it. Let's just say it is 999, or you can call it infinity in computer science terms. And root.left bit is going to be 0. Root.r bit is going to be 1. You'll realize why I did this just in a few seconds. Root.left equal to root.right equal to root. Okay, it's going to point to itself. This is the ternary operator, and you can do this, so don't worry about it. This is how the real root looks like. 999 is the data, 1 the R bit, 0 L bit, and it points to itself in both directions, the root. So what are the conditions? We need to add new roots. So we create a node. This is a create node function. I'm going to declare it in a few moments, and you just add a few elements in that node and create a tree. And these are for printing these system calls are basically printing it out on the screen. And this is different kinds of in-order and pre-order and post-order printing mechanisms. Those functions are declared later. We'll get to them. This is just the main function, and we're going to deal with it. Okay, no big deal. Now let's start with something that is a bit of housekeeping stuff, the housekeeping variables. Now these are declared before the main function inside the class: static node root, static node current, boolean direction right, and boolean direction left. We'll get to them later as we proceed through the functions. Now public static void create node. So what do we do over here? Now we take a parameter int node. As you saw in the main function, I created nodes. This is that function. So node equal to new node data. We have seen this before. This creates the node instance and allocates memory to it with the new keyword. So now let's see. Root.left equal to root, and root.right equal to root. What this means is that if root.left is equal to itself and root.right is equal to itself, just remember, as you saw before, when we made the root, the real root, we initialized it and pointed all the pointers which it had to itself. So this condition in that case becomes true. So this is the first block which is going to be executed. So we're going to say node.lbit is equal to root.lbit. Now let's just go forward and I'll show you what's happening. Okay, so basically what happens is that when you say node.lbit, this is the node and this is the root. Okay, so you said node.lbit. Now node.lbit is this one. Initially this value was 0. If you go to the previous slide, you'll realize this value is 0. So I initialized this to 0. Then I came over here, node.left equal to root.left. So what is node.left? This is node.left and it points to root.left. Okay, that's true. Root.left equal to node. And root.left is equal to node. See? And root.lbit should be equal to 1. Okay, done. Node.rbit should be equal to 0. Okay, done. And node.right should point to the root. Okay, now this over here is basically our virtual root. This is the real root, this is the virtual root, from where we are going to start building the rest of the tree. We're not going to build the tree from here, but we're going to build the tree from here. Why we do this? Simple, because we need somewhere for the threads to point, right? We can't just point threads to random locations when they are null and they don't have a valid predecessor. If they have a valid predecessor, they can point to itself, point to that. But if they don't have a valid predecessor, they can't just point anywhere. The whole point of the threaded binary tree is to have no null values. Also, the whole point of the threaded binary tree is to loop through it easily and without using recursion. Yeah, well, that's the whole point, to not use recursion. That is the concept of threaded binary tree. As you have seen in the previous, the regular binary tree, we use recursion in order to produce the in-order, pre-order and post-order lists. But here we don't need to use recursion. We can do it with a simple, I can't say simple, but a relatively faster process by using a while loop. So let's just go to the else part. Now, if this condition is not satisfied, then basically we need to find where the particular node is. Now this is just a binary tree. If you remove all of these arrows and allocate them as being null, this is going to be a regular binary tree. So we can find values greater than or less than and just allocate them according to what we did in the binary tree tutorial. So let's do that. While true, if node.data is less than current.data, then you would have expected it to go to the left. Yeah. If it direction left equal to true, okay, then break. Else, if the current.current.left, yeah. So if node.data is less than current.data, current is the new node, and if current.lbit is equal to 0, then direction left is true and direction right is false, because you want it to be in the left direction because it's less than. Okay, else if that's not the case, then you move on to the next node if it exists. If current.lbit equal to 1, which means that there is a child node, so you move left. If there is no child node, it means that current.leftbit is 0. Simple. Then else if current.rbit is equal to 0, which means that there is a thread, you can allocate the direction right as true and you move to the right. We'll get to what direction right equal to true means. Else current.right is what we need to go, because if rbit is equal to 1, we need to go to the right end of the binary tree. Similarly, if the direction left is true, this is the entire thing. So suppose direction left, which means that we are going left. This is the real root, the virtual root, and this is the new node that is in the left direction. So node, this is the node and this is current. This is current, this is the node. And if you follow these instructions, they will make sense over here. So we are attaching it to the left end. The left is pointing to the node. And if you come over here, the right direction, the right is pointing to the node. And you can follow these instructions. Now basically these instructions are not random, they're properly thought of, but they make sense. See, when you do node.write bit equal to current or orbit, now you want them to have the same orbits because they are the root node in the right direction, so you would expect them to have the same orbit. Now node.write equal to current.write because you want them to point to each other, but in this case what happens is that the node has a parent of the root. It's a thread, it should point somewhere, but it can't point to itself because this does not occur in the in-order successor of the list of the binary tree. It should be pointing to the one to which the current.write points, which is the physical main real root and not the virtual root. Okay, so similarly current.orbit should be 1 because now it has a child node and it's not a virtual node anymore, and node.lbit is 0 because it doesn't have any child nodes, and node.left, this is the node.lbit, and node.left points to current because that is the parent. Else you move in the right direction and that works too. So else if there's nothing happening and the tree system is breaking apart, you actually have to print out system.out.println program is a fail. I mean, that's not what you need to print out, but in this circumstance I'd go with that. Then system.out.println nodes added, and yeah, that's about it. So let's start with the in-order listing because we want to prove that this program actually works and not just sit around and connect nodes. Current.root.left. Now I told you that we will start building the tree with not the real root but the virtual root, and the virtual root is on the left of the real root, and as it was defined, root.left is the virtual root, so that is what we're going to assign to current. While current.left bit is equal to 1, which means while current.left bit actually has a child, move left. Okay, and while current is not equal to root, okay, once that, see, if while you're moving left, somewhere some node is going to have a pointer which points to the real root. Now if it points to the real root, you don't want to go there. So once it comes out, while the current is not equal to root, system.out.print current.data, current equal to next in order current. So once you do this, you actually have to figure out which the next in order element is going to be, because that's how you are going to print it out, right? So that is defined in the next slide. That is node next in order, which returns a node to this current value over here, which goes again through the loop. So let's do that. Next in order, if current.orbit is equal to 0, return current.write, and current equal to current.write. Now the same thing, if current.orbit is equal to 0, which means that it has no real child nodes, okay, on that particular thread, so it returns that particular value, and then you check return current equal to current.write. If this condition never executes, the return never shows, you go to this particular statement, current equal to current.write, and then you're like, while current.lbit is equal to 1, the same thing which we did in the previous function, current equal to current.left, and then return current, because that's going to be our, so the whole point of this is we don't want to use recursion. We want to use functions to get the next value which we're going to print, but we're not going to use recursion over here. Okay, now in this we're going to use a recursive statement. This is a very simple statement. This is the same as that of our previous binary tree statements. So if you want to go in detail, you have to actually write this down on a piece of paper, draw a few nodes and connect them and disconnect them, because me sitting here telling you is not going to help anything. Actually, I'm just giving you the code and just, you know, explaining it on top, but the real deal is you taking a pen and paper and drawing stuff. So this is the recursive function, which is the same as the binary tree, and yeah, that's about it. Thanks for watching. If you like this video, share, subscribe, and you know, learn some new stuff. Thanks for watching. Later, guys.